Talking a little bit about speed in space and resistance of an object that's orbiting around a central object. And the hypothesis that Hannah has brought forward is that microgravity will create less resistance against the object in motion, and so it will travel faster and farther than it would in gravity. And in Hannah's experiment, she actually had the object orbiting around in a plane that was just above the floor and timing the distance that it traveled before it fell to the ground. So since we have no gravity here in space, we're going to do the experiment a little bit differently. And since we'll actually be using, this is the deck location in the Node 1 in the space station, and since we have no gravity, any of the four walls in the space station could be used as the floor, or essentially be considered the floor. So we won't have a gravitational force pulling the eraser towards the floor, but we're going to have the object orbiting in the central part of the node, and just to show you that gravity has no effect while we're in space, but we do still have drag here in the air that's inside of the space station, and so we should see the object rotating and continuing to rotate around the central object, and then possibly slowing down as we increase the number of orbits due to drag on the orbiting object, which happens to be an eraser. So just like Hannah had proposed, we've taken a tape measure, ordinary tape measure, and we've situated it to the floor here, and we're going to wind it out. Our first little taped experiment is part of the experiment is to pull the tape measure out 1.5 meters. So I'll do that right now, and then we'll time the amount of time it takes for this tape measure to close, so we can calculate that as far as the initial force that's on the object.
For the red satellite, I've got the serial barcode numbers for the batteries. We are ready to go. Okay.
Okay, that's 1.5 meters of tape, and you can see the end of it there. And I'm gonna depress on the count of 3. And my mark, I'll depress the return switch on the tape measure, and we'll time the amount of time that it takes for the tape measure to close. Okay. And my assistant, Tracy Caldwell, who's behind the camera, waving hello, she'll be helping me, assisting me with the timer. And also be ready at home to time this as well, so we may need your backup as the amount of time it takes to close the tape. Okay. All right. Okay, we ready? Get those timers ready, and it'll be a 3 count, and then my mark. 3, 2, 1, mark. Okay, it's a pretty quick return, and so we'll try it again for those timing at home. It's very difficult to do here in space, and Tracy's being so good about holding the camera for me. So not a. Okay, yeah, it's less than a second. So if you have a stopwatch, again, it'll be on my mark, and then you can see the end of the tape right here when it hits. So, okay, be ready on those timers. And 3, 2, 1, mark. Okay, too fast to really time in space, and so if you got that at home, it's somewhat less than a second. So that'll give us an initial indication. Now, just as Hannah had proposed to set up the experiment, I've taken I've taken 2 rolls of 14 cotton swabs that you use to clean your ears, And we've wrapped them in gray tape, and then taken a second row of those, and we've taped those together to form a hard surface, just as Hannah had proposed. We're going to, this is going to be the surface that's going to impact our orbiting object, which is an eraser in this case. And we'll go ahead and attach this to the end of the tape measure now.
Station 1-2, battery serial numbers for the blue satellite. Alright, PSI 02220J and PSI 02226J. We copy that?